So in today's lecture, we are going to talk about the basics of digital communication systems. And this will be an introduction as well as some details about the basics of modulation schemes in digital communication. So as we know, before digital, we have analog. And the key difference between analog and digital is that analog takes continuous, infinite amount of values. It's continuous. At any point of time, at any instant, you have certain value. While in digital, you are limited to a discrete number of values, like 5 values, 8 values. Your signal cannot take any value. And due to this reason, the detection process of your communication system turns to be easier than analog. For example, at the receiver, if you can see with me on this picture, what do you see here? You see a pulse, we are transmitting it over a channel. The channel can be wire or waveguide or media or whatever. And the communication system can be satellite, can be mobile, can be TV, can be any communication system. And this system assumes that's transmitting a pulse. And the pulse at the transmitter, at the time you send it, the pulse is perfect, has no distortion. It's pure rectangular pulse carrying your data or representing your data. After you send it over the channel and you come and see this, visualize this, this waveform using spectrum analyzer after 10 kilometers, for example, you might see some slight degradation on the rectangular pulse. The rectangular pulse is no longer a rectangular one, it's distorted. As the signal goes and it travels, the distortion increases. By the time it reaches the receiver, the signal becomes almost, if the distance is really large, becomes really difficult to detect and see and extract the information from it. Now, in analog communication, it's extremely difficult to detect, to generate or receive the signal that you have transmitted over a long distance if it goes through all these kind of degradation. And the degradation, as we know, happens due to electrical noise, the non-ideal frequency response of the circuit and the cables, and fading, dispersion, and money phenomena. So due to all these phenomena, your signal can reach the receiver with a very bad quality. And the role of the receiver here to be able to regenerate, reborn this signal one more time from the observation that it has. So if it was analog, if the signal is below the noise or the receiver is not able to see it perfectly, the receiver will not be able to extract the data from that signal. While in digital communication, even if the pulse is degraded, the receiver knows ahead of a time that this pulse can take a finite set of values. So all the receiver needs to do is to search for the closest possible value, the closest possible waveform to this signal, and see whether it's matching with the current received signal or not. And if it is matching, then most probably this is the signal that I have transmitted. So this is the motivation behind digital communication. Digital communication, it's easier to regenerate your data even if it gets distorted by the channel and noise. It's easier to process it because you transfer it to digital, and computer systems are digital. If you want to run an algorithm to perform some processing, to encrypt the data, to secure the data, it's all done in digital. So it's more robust against the impairments of the channel. You can process it the way you like and make it more efficient. This is why we move from analog to digital. So now this is why we move from analog to digital, but the question is, what's the basic digital communication system? Can you give me an example of a communication system that can ensure transmitting and receiving your data successfully in spite of passing through some impairments and noise and degradation? So assume you are transmitting data, and this data representing a video, a voice, a signal, whatever. And the way we process this data and transmit it is as follows. You take the data and you encode it. We call the first encoding process source encoding. And source encoding is responsible for compressing your data and so that its size becomes small and you can save it in a memory size or small size, and you don't need too much bandwidth to transmit your data over it. So these are the two key reasons why we use source encoder. And this can be a question, for example. Anybody can ask me this question. Why do we need source encoding? Source encoding takes a packet, a random amount of data, let's say 100 bits. And after the compression process, these bits turns out to be like 50, 60. So it reduces the size of your data. When you reduce the size, you don't need too much memory and you don't need too much bandwidth, because memory and bandwidth, they cost you money. And the goal of designing any communication system is to ensure that it works fine, but also with minimal amount of money, because this is how I can compete with the companies who are producing similar systems to mine. After that, we encrypt our data. What's encryption? We said we encrypt our data means we manipulate the data in a way that any other receiver than the illegitimate receiver, he cannot access the data without our permission. And how do we do that? We share a secret key between the transmitter and receiver ahead of the time securely. We assume that only the transmitter and receiver knows this key, and they manipulate the data with this key. For example, you know the XOR operation or NOR or any operation you like, and you end up getting a sequence. This sequence is random. This sequence is nonsense, meaningless if you don't have the key that was used by the transmitter. So at the receiver, the legitimate receiver, since he has the key, he just reverses the process that the transmitter did at his side, then he will get his sequence perfectly. While another illegitimate receiver, a bad receiver we call it, who wants to access your data, he will try to access the data, but the data, no matter what method he tries to decode and detect the data seems meaningless, doesn't represent meaningful information. And due to this reason, he cannot decode his data. Why? Because he doesn't have access to the key so that he can reverse the process successfully. After encryption, we have channel encoding. What's the purpose of channel encoding? The purpose of channel encoding is to protect your data against the noise in the channel or the impairments in the channel. For example, assume you are transmitting a sequence of bits, and this sequence, all of a sudden, some of the bits have gone through like too much noise and too much fading. At the receiver, you cannot decode your data if it goes through receiver. So what we do, we add some redundancy. And these redundant bits are capable of correcting your transmission. So even if you make some mistakes, due to these redundant bits, you can recover your transmitted bits successfully. After this, we said we use multiplexing from other sources. let's say we want to transmit if from this source and this source can be a user, can be a device, can be another stream of data. You need to serve all these devices or users or data streams together or applications. You just need to combine them. How do you combine these data? How do you sort them? With many techniques. Like you can sort them in time, put them back to back in time, put them back to back in frequency, put them on top of each other in power, put them on top of each other in code. Whatever mechanism you use, the goal here is to be able to put the data coming from different sources together without causing any interference, and you make sure that the receiver can decode his personal data, his intended data, successfully without getting the interference from the other users. So this is the goal. After that, we have pulse shaping, and the goal of pulse shaping is to limit your transmission in time and the frequency, so that you don't interfere with the other users who are transmitting at a different time or at a different frequency, and you also make sure that you don't consume too much bandwidth. After that, you have the bandpass modulation, and in this case, you map your bits. Bandpass modulation. You have a sinusoidal carrier. We know that modulation. What's modulation? Modulation is basically changing the properties of the high frequency sinusoidal carrier according to the incoming data information or data bits. This is the basic definition of modulation. So at this point of time, since I'm gonna use sinusoidal carrier to transmit my data, I need to change these properties of this sinusoid according to the data stream I have. So assume I'm using amplitude modulation or phase modulation, phase shift keying. You need to change the phase of this sinusoid according to the incoming symbols. Yes, this is practical. This is at baseband level. And then you have frequency spread. We said that we really need frequency in some systems. It's not necessary block actually, but we need it in many cases where we need to minimize the interference. And to understand this and why we need it, assume the case where you have severe interference at a certain frequency, F1. And you are transmitting over this F1. Definitely the receiver will not get any information over that frequency because there is too much interference. However, if you make your communication jump or hop from one frequency to another over a certain period of time, then you, instead of occupying this bad frequency all the time and getting bad performance from it, you just occupy it maybe 10% of the time. So your degradation will be 10%. Assume you are transmitting 100 bits. How many bits you will lose? Just 10, because you are transmitting 10% of the equivalent. But assume you are not using spreading and there is interference over that channel. You are locked to that frequency and there is interference. Use whatever number of bits you send, no matter what protection or what mechanism, you will not be able to decode your data successfully. And this can reach to 100%, which is so bad. That's why we need spreading. Military uses spreading because in military, in war, in this, too much interference, too much. And the other goal for spreading, it's also kind of security, because when you spread your signal, we said then, like if you remember with me, when you spread your signal, what happens? Suppose this is your signal, right? After spreading your signal, and this is the level of noise level is such. After spreading your signal, what will happen? Your signal will become wide, extremely wide, with little amplitude, and the noise will be above the signal. So nobody will be able to detect your communication. Nobody would know that you are communicating or doing some communication. And that's kind of security. If they don't know you are communicating, can they interfere your communication? Can they block you? They cannot. In military, what do they do? For example, they want like to track a plane, to cut the communication on a plane, or to cut the communication with the soldier in the battle, or whatever reason. They have spectrum analyzer, a device, and this analyzer, you put an antenna to it, and you can capture all the signals on the air. And since the signals are propagating in omnidirectional way, the signal, because of the environmental reflection, you can see most of the signals if your receiver has high quality. So an engineer can identify that at this frequency there is communication, there is a signal going forth and back on this signal. Then he understands that there are some people communicating over this frequency. I want to cut their communication. What do? I bring another transmitter and send another signal, any signal, at the same frequency with higher power. So their signal, let's say the signal of the users who are communicating has this power at frequency F1. To block their communication, what do? You bring a transmitter, a generator, and you transmit a signal of higher power at the same frequency. So those guys will not be able to receive their own signal, the purple one. They will see this signal, and this signal is random. They generated it, their enemy generated. So this is how you can block a communication. This is how of course, all the vehicles, planes, I mean, most of the server, they need communication to perform their task perfectly. So you can, with this clever. To avoid this hack, what do? They use spreading. Spreading because it goes below the noise, and the guy who has the spectrum analyzer cannot see the signal. In USA, for example, you can get a license to transmit signals, like driving license, to transmit signals, receive signals, analyze signals, but without interfering with other. Like, be able to transmit and receive without interfering with others, because if you interfere, it's like making an accident, and they will go to the court and make a case against you and say he interfered with our communication, his intention was bad to cut our communication, and he will sue you, and the government may fine you, may charge you money because it's like driving. You don't need, while you are transmitting, you must not interfere with anybody, because this is my land, this is my area. If you come in my way, you cut my communication. If you cut my way, you make an accident with me. That's serious. Now another guy may come and say, okay, if you know the codes, you can use the same code and generate the data, but this is advanced level, we can talk about it later. And last block, we have multiple access. Multiple access, we said it somehow has some similarity with multiplexing, but here we have with users. We have multiple users, and multiple users want to communicate over the channel, and you want to serve all of them fairly. So you need to distribute this communication between them. And the way you do it, whether in time division multiplexing, frequency division multiplexing, code, power, whatever. And now you send your signal to the antenna, and the antenna, what does the antenna do? just to propagate an electromagnetic wave. What you produce here up until here is electrical signal. Electrical signal that has many changes in its features, like amplitude or phase or frequency. These changes when it goes to the antenna. Antenna is a passive element, dummy element, doesn't do anything. Antenna just when an electrical signal passes through it and an electromagnetic signal propagates. And these changes in the electrical signal, they are like your fingerprint. They will appear in the electromagnetic signal. At the receiver side, here, the receiver has an antenna. When an electromagnetic signal hits the antenna, touches the antenna, an electrical signal will be generated. And the features of that electromagnetic signal will be transformed to the electrical signal. So, from electrical signal, you go to electromagnetic, and from electromagnetic you go to electrical again. And from electrical you go all the way here to the receiver until you receive your bits, and these bits again make them video or image or audio or voice or text or whatever application. That's the magic of communication. So at the receiver side, after the antenna, we have the opposite of each block we have at the transmitter. You have multiple axes, you have multiple axes. Let me explain to you, for example. The users here, for example, let's say 5 users, and to share the communication between them, we assign a code to each user. We assign a code. A code is like a language. You understand German, and your receiver understands German. So all the ones who don't understand German, they cannot get the communication. You talk Japanese and your receiver talks Japanese. All the ones who don't know Japanese, they cannot understand what you are talking. Although the same communication, everybody is talking together, all of them, but your ear gets synchronized to the one who talks your native language. That's the rule. Here, what do? The Japanese guy, we give him a code. It's like this, that enables him to synchronize to the Japanese language. And the same with the English, the same with the German, the same with the French. You understand the concept, but the opposite. Here you use the code, suppose you multiply, there you divide, or you do the opposite, the reverse. Here you have frequency spreading. At the receiver side, you have despreading. Your signal here became below the noise. After you multiply it with the code at the receiver, the signal returns back to be just like this. Just like this, after you multiply it by the code. You have modulation. At the receiver, you have demodulation. You have the carrier sinusoidal signal, which is electrical signal now. You need to get the complex symbols from that sinusoidal signal. Now, after the modulation process here, you don't have signals, you have math, you have complex numbers, and these complex numbers carries the information that was represented by sinusoidal signal. After this, you need to detect. You have, for example, if you are transmitting 16 QAM, how many different symbols you have? 16. You need to compare with all these 16s your received signal, your received symbol. You need to compare it with all these 16s and see to which one of these 16 symbols this signal is the closest. You compare with the first one. How do you compare? You just do subtraction, for example. For example, I receive this data R. This is R hat. Yes? And I subtract it from the possible symbols. SI. I have 16 symbols. Yes? I just for loop in programming you write for loop. And for example, this is the received signal. This is what I receive. I cannot do anything about it. Now I go take the first symbol, the first possible. I know the possible values because this is what digital communication is. You have a set of possible values, a set of possible waveforms, and your received symbol must be one of these waveforms. So you are limited. You just need to compare, find out which one. You have 16 and you have received this symbol. Find out this symbol, which one of these 16, after it passes through the noise and channel and degradation and impairments. This is the goal of the receiver. And this is really challenging. You need to produce algorithm, good algorithm that can produce this. You just for loop, you compare with 1, you compare with 2, you compare with 3, you just find the result. The result, say, for example, the result is K1, K2, K. Now find the index of K that has the lowest value. The index of K that has the lowest value means was the closest to the received. Yes? The closest to the received, then I will now make my decision. This is the symbol that the transmitter has sent, most probably. We will talk about this in detail. This is just scratching the surface. This is like the roadmap of the book, this figure. Each block is going to be chapter or 2. At the end of this course, you will understand all these blocks in detail. But here we are giving you a general overview, umbrella about all the most of the transformation blocks that are involved in the process of transmitting your data digitally. After you detect, you have here, if you use multiplexing, you can use demultiplexing, the opposite. I told you, if you use channel encoding, you need also to do channel decoding. Here, the responsibility of this block to reduce the amount of errors. Detect the error and correct it. You must be able to know that you have made an error, and you have to have the capability to correct that error. See, this is the functionality of this block. So important in the communication system, because we are always susceptible to errors. And we need to fix these errors. We need to eliminate them. And you cannot eliminate them unless you find them. And this is what this box does. After channel decoding, you need to do the opposite of encryption, which is decryption. And after that, you need to do the opposite of source encoding, source decoding, and then formatting, and this and that. As you know, the blocks which are hashed, they are optional, and the blocks which are not hashed, they are essential to making a communication system successful. So all these blocks deals with bit stream up until here. Yes, and here we have waveforms. Digital. You got me? Everybody focusing with us? Here, see, from here, source encoding, encryption, channel encoding, multiplexing, till this level, we have bits. After this level, pulse modulation, you convert the bit to pulses. You have here digital baseband waveform. Digital baseband waveform, give me an example. Rect, sync, raised to sine, these waveforms. Because I told you we need. And after that, we have digital bandpass waveform. Bandpass waveform like sinusoidal signal, sine and cosine. And you have here the channel impulse response. Here you have electromagnetic equation, electromagnetic signal. The things that we studied in electromagnetic 1 and 2. Here in the channel. So this is the basic thing, the block diagram of a typical digital communication system. This is what we are talking about, and these are the important blocks of this communication. Any questions so far? Everything is fine? Yes. Here, essential. Yes. Yes, that's right. Essential. With them, you can be able to transmit your data. But with errors, without security, without robustness to interference, without being efficient in communication, without. Nobody wants his communication to be like this. Yes, you can communicate, but this is not efficient, good communication. That's why we need to add all the other blocks. And plus, in your project, we have to come up with other blocks. Insert your blocks here, for example. Other blocks, we insert them here. Your goal, your project is going to be invent a new block where we put it somewhere here, and this block is going to give us more advantage. It's not essential. You tell them, look, my block, you can't communicate without my block. People are communicating. They have devices. They have communication. They have tools. But if you use my block, you will be able to transmit your data faster, low latency, low errors. If you market, if you say to any company like this, the company will be interested in your block and they will pay you money to implement and buy your block. But be able to come up with a block that brings advantage. It's not essential. Communication systems are working with you and without you, with your block and without your block, with subcarrier number modulation and without, with antenna number modulation and without, with power number modulation and without. These are the techniques, I'm naming techniques of some of the techniques that were implemented by your previous friends. Students who took this course with me before. So this is the basics. These are the things I want you to understand. So we can stop here, take a break for 5 minutes, and resume again. Thank you.